Okay, good morning to everybody or good afternoon and good evening na rin kung anumang oras nyo pinapanood tong video. So let's proceed to the next chapter 4, that is fluid flow in pipes. Okay, and we will be needing, of course, the concepts we have learned before in chapters 1 to 3. So I hope you have mastered already, applying the different concepts from those chapters. So this time we will be dealing with fluid flow in pipes. Okay. First, we need to define what is a pipe. So a pipe may be defined as a closed conduit through which liquids or gases flow. In our subject, of course, we will be dealing with flow of liquids, particularly water. No? In hydraulics, pipes are commonly understood to be conduits of circular cross-section which flow full. So it is usually circular. I think I have explained why circular before. Bakit siya circular? Usually hindi siya rectangular or square or any other shapes. No? So I have explained already kung bakit circular yung mga pipes natin. And another condition is that for it to be considered pipe, it should be flowing full. No? Conduits flowing partially full are considered to be open channels. So ano yung mga conduits flowing partially full? Ibig sabihin merong surface ng liquid, no? And the surface is usually exposed to the atmosphere. Okay? So those are considered to be open channels. So we will be discussing open channels in a separate chapter. So pupunta tayo dyan later on. Okay? So under fluid flow in pipes, we will be dealing with the computations of major head losses and minor head losses. Okay? And there are things that we need to know, to compute for these head losses or energy losses. Okay? And ito, yung mga concepts na kailangan nating maintindihin. First is laminar flow. What is laminar flow? The flow is said to be laminar when the path of individual particles do not cross or intersect. So ano ibig sabihin nun? Say for example, we have a pipe and a certain liquid flows in it or through it. So yung path ng individual particles, we call those path lines or streamlines. Path lines or stream lines, these are imaginary lines which are drawn to somehow identify yung path ng particles ng liquid. So for example, meron tayong mga streamlines or path lines dito that is used to predict predict the path of individual particles, yung mga path lines natin. So this is not really visible, but we draw that to identify the path lines or streamlines. So when the path lines or streamlines do not intersect, that means parallel yung mga yan, that means the flow is said to be laminar. And itong klaseng flow na to is very very slow motion. So usually yung mga yung flow dun sa gripo ninyo sa bahay ninyo or yung mga flow natin sa mga water lines natin, usually those are turbulent flow. So okay. And laminar flow, so the flow is said to be laminar when the Reynolds number is less than 2000. Okay, the Reynolds number is less than 2,000. If you try to read other books, fluid mechanics or hydraulics books, hindi siya 2,000 ano. Yung iba it's 2,100, yung iba naman ay 2,300. So iba-iba no. Bawat author ay iba-iba yung boundary na nilalagay. But in our class, in this subject, in our course, let's just agree that if it's less than 2,000 yung boundary natin between laminar and turbulent. So if less than 2,000 yung Reynolds number, that means the flow is laminar flow. Okay? Next is turbulent. Turbulent is the opposite of laminar. That is when the path lines or streamlines intersect. So ibig sabihin, mabilis na yung flow, such that the path lines of individual particles are nag-intersect na mga yan. Okay, that is when the Reynolds number is greater than 2,000. Okay, so this is turbulent and this is laminar. Ano bang importance ng pag-identify whether the flow is laminar or turbulent? This would be very important when we compute for the major head losses or frictional losses sa mga pipes. Now, we will try to discuss that later. So for now, we need to know how to identify the type of flow, whether it's laminar or turbulent. Sir, what if the Reynolds number is equal exactly to 2,000, or although this rarely happens, this is a critical flow. Critical flow. And the velocity when the Reynolds number is at critical condition or 2,000, we call that the critical velocity. So yan yung boundary between laminar and turbulent. Okay? So that's it. Next would be Reynolds number. So the Reynolds number is dimensionless. So take note, dimensionless ratio of the inertia force to the viscous force. It's a function of the viscosity of liquid. So somehow the flow to the viscosity of the liquid affects the type of flow, you know, yung flow ng liquid. So Reynolds number is computed in terms of the absolute viscosity or the dynamic viscosity and the kinematic viscosity. So ito. So the Reynolds number is a function of the velocity. Okay. So pag mas mabilis yung flow, that means mas malaki yung Reynolds number, the diameter also. The density, of course, it is inversely proportional to the viscosity. So pag mas viscous yung liquid, that means mas mababa yung Reynolds number. So this is the velocity, the diameter. Now you can express, pag hindi circular yung pipe, you can express the diameter in terms of another value, which is the hydraulic radius. We shall discuss that a little later. Then in terms of the kinematic viscosity, okay, ito yung kinematic viscosity. This is the dynamic or absolute viscosity. So dynamic viscosity is sometimes called the absolute viscosity. This is absolute viscosity. Yeah. Okay, that's how we compute for the Reynolds number. So if we're done computing for the Reynolds number, we can easily identify whether the flow is laminar or turbulent, and we can compute for we will know which formula to be used in the computation of the energy losses. Okay. Yan, so yan yung importance ng mga concepts na ito. Okay, next is when the pipe is not circular, how do we compute for the Reynolds number? So for non-circular pipes, so instead of using D in the formula, we can use the hydraulic radius. D is equal to 4 times the hydraulic radius. So yung hydraulic radius, that is the ratio of the cross-sectional area of the conduit. So pwedeng rectangular, square, or any shape, divided by So cross-sectional area divided by the wetted perimeter. So take note, this is the wetted perimeter. Okay, since we are dealing with pipes naman, the wetted period and the flow is full, na punong-puno yung pipe. That means the wetted perimeter is also equal to the perimeter of the section. Okay. Sa channels kasi hindi, no? So yeah. So that's it. So pag hindi circular yung pipe, we can, instead of D, we can use the hydraulic radius to solve for instead of D, no? To solve for the Reynolds number. Okay. Okay, next concept is the computation of head losses in pipe flow. So we have two head losses. When we say head loss, we mean energy loss, no? Loss of energy. Okay, so we have major loss and minor loss. Major losses are usually due to friction. So if we have a conduit or a pipe, nagkakaroon ng friction dun sa may wall ng pipe. So between the particles and the wall of the pipe. So somehow it depends on the roughness of the wall of the pipe. Ano? Yung mga particles dito, usually sumabagal yung galaw ng particles near the pipe due to friction. Ano? So itong mga particles na yan, usually sumabagal yan. So if you plot the velocity inside the pipe, so yung pinakamabilis of course ay under normal conditions, yung pinakamabilis ay nandun sa may gitna, yung mga particles sa gitna. Ang pinakamabagal of course ay nandun sa gilid because na-experience nila ng resistance dito sa may gilid, and meron corresponding loss of energy because of that resistance, and we call that the major loss or loss due to friction. Okay, yan ang nangyayari. And minor loss and major losses. So in the study to determine the loss governing the loss of head due to pipe friction, it has been observed that the resistance to flow is, so na-identify dun sa modules natin. So this is true to all major head loss formulas, no? Sa subject na we're going to discuss tatlo yung mga commonly used na ginagamit sa commonly used formulas to compute for major head losses or friction losses. Okay, so number one, the major loss or loss due to friction is directly proportional to the length of the pipe. So pag mas mahaba yung pipe, ibig sabihin mas malaki yung loss of energy, no? Second, the major loss varies or varying to a certain power of the mean velocity v. Okay. So it's also a function of v of the velocity. So pag mas mabilis, that means mas mabilis, mas malaki din yung loss of energy. And number three, it is dependent on the pipe wall's roughness only under turbulent conditions, no? So the roughness of the wall of the pipe, no, that somehow contributes to the loss of energy. Kapag mas smooth yung wall ng pipe, that means mas maliit yung loss of energy. Pag mas rough yung wall ng pipe, that means mas malaki yung loss of energy. In the major head loss is also inversely proportional to some power of the diameter. So pag mas malaki yung diameter, mas maliit yung loss of energy, no? Then 5, it is independent of the pressure which affects fluid motion. So the major loss, the pressure inside the pipe, has nothing to do with loss of energy. Although most of the time we express the loss of energy in terms of pressure. So we call that the pressure drop, no? So kapag nagkaroon ng pressure drop, ibig sabihin may nagkaroon ng loss of energy. So we usually express loss of energy in terms of pressure. We call that pressure drop. No? So that's minor loss. So ay major loss. Major loss due to friction. Ito yung medyo madugo kasi we have formulas, derived formulas to solve for the major losses. Ganun din naman sa minor loss, but that would be easier. Okay, ano yung mga minor losses? No? Minor losses caused by the following. Due to contraction of cross-section. Ano ba yung contraction? For example, meron kang pipe, naglagay ka ng reducer, so lumiit yung cross-section, so merong corresponding loss due to contraction. So pwede rin naman na sudden contraction. So malaki, biglang lumiit yung pipe, so merong corresponding loss of energy because of this or sudden change of velocity. So yung mga minor losses usually is caused by changes in terms of velocity, yung direction ng flow, ganun. So yung minor losses. Another is due to enlargement. Minor loss due to enlargement. So biglang lumaki yung cross section ng pipe, so may flow dyan. Biglang lumaki yung cross section, there's a corresponding loss of energy because of that. No? Depende pa yan kung sudden yung enlargement or gradual siya. So kapag gradual, usually mas maliit yung loss of energy. No? Okay, next is minor loss due to obstructions. Ano yung mga obstructions? Pag nag-travel yung particle ng liquid from one point to another, and then may obstruction in between, usually caused by mga valves or gate valves. Okay, ito yung mga, depende pa yun kung yung valve ay half closed or 1/3 lang yung closed, so may corresponding loss of energy because of these obstructions. Okay, so what last would be the minor loss due to bends or curves. So pag may mga 90 degree 45 degree curves tayo, may sudden change of direction, yan, so may corresponding loss of energy because of those changes. And we always express minor loss in terms of the velocity head. Since minor losses are usually caused by changes in terms of velocity and direction of flow, so minor losses are oftentimes expressed in terms of the velocity head. Okay, yan. So ito yung mga nagko-cause ng loss of energy. We have major loss and minor loss, and later on we will discuss, i-apply natin na sometimes or most of the time we neglect minor losses. If we analyze complex piping systems, we oftentimes neglect minor losses, no? Okay, and consider only major losses sa computation ng energy loss or head loss in a certain piping system. Okay, another consideration also is the shearing stress in the pipe. Shearing. So nagkakaroon, so since meron tayong resistance doon sa may pipe dito, sa may wall ng pipe, meron tayong shearing stresses dyan na part. Okay, and sometimes if the pipe, kung yung pipe natin ay it's not strong enough to resist yung shearing stresses, okay, pwedeng mag-fail yung pipe natin. Okay, so that's why importante, we need to know the stress or shearing stress experienced by the wall of the pipe so that we can decide what material to be used sa pag-lay ng pipe, kung PVC or GI pipe, steel pipe, and other types of pipes in terms of material. So we can compute for the shearing stress in terms of the loss of energy or the head loss, no? Kasi nga yung loss of energy natin, yung frictional loss, we can convert that or we can express shearing, connected kasi yan, no? Yung friction dito ay connected din sa shearing stress experienced by the wall of the pipe, so we can express the shearing stress in terms of the loss of energy, especially yung loss due to friction, no? So shearing stress, tau is equal to gamma, yung loss of energy, this is loss of energy due to friction, times the diameter all over 4 L. So yung head loss diameter, we can express, if the pipe is not circular, then we can express D in terms of the hydraulic radius. L would be the length of the pipe. Okay, so that's it. Okay, and we can also compute for the shear velocity, no? Shear, so that we can limit the velocity, since it's a function of the velocity. We can limit the velocity of the pipe to prevent it from failing due to shearing stress. So we can compute for the shear velocity. It's tau, square root of tau all over the density of the liquid. Okay, or that is also equal to velocity times the square root of the friction factor all over 8. We can compute for the friction factor using several formulas later on. Friction factor, we can compute for the friction factor using several formulas, discuss natin mamaya. Okay, okay. 8 ito, hindi gamma. Okay, so that's it. Ano pa yung mga ibang concepts? Yun lang. So yan, so sa chapter ito we will be computing major losses, minor losses, and shearing stresses, and also Reynolds number, but automatic naman na yan, yung Reynolds number. Okay, so let's proceed to the different formulas used in computing major losses or losses due to friction. So number 1 is yung pinakasikat. Okay, the first one is the Darcy-Weisbach formula. Darcy-Weisbach. So the head loss, based from our initial discussion before about the nature of the computation of head loss, head loss due to friction is equal to, we have F L over D times V squared all over 2G. So L is the length of the pipe, velocity, diameter, and F is the friction factor. Okay, this is applicable for both English and the SI system of units. For laminar flow, the friction factor is 64 over RE for Darcy-Weisbach. For Darcy-Weisbach, for laminar flow, the friction factor is 64 all over RE. That is when the Reynolds number is less than 2,000. So for turbulent flow, where the Reynolds number is between 3,000 and 10,000, the friction factor is computed using this derived empirical formula. We have this formula. Okay, and for circular pipes in the SI system, in terms of discharge, ito kasi in terms of velocity, but oftentimes you compute it in terms of discharge. So that's equivalent to 0.0826 FLQ squared all over D raised to 5. That's how we compute for the head loss due to friction using Darcy-Weisbach formula. Take note, this is in SI, derived using the SI units, and it should be circular pipe. Okay, now what is this friction factor? Ito medyo mahirap na i-compute unless given na sa problem yung friction factor, but oftentimes in many books, fluid mechanics or hydraulics books, meron ng values ng friction factor, nakatabulate yan in many books. sa fluid mechanics. So kung hindi naman friction factor is computed using certain formulas and Moody diagram or Moody chart. Okay, we can solve for the friction factors or for Darcy ways back. We can solve for the friction factor in terms of the Moody chart or the Moody diagram. Yan. Moody. Tulad ng mga girls, Moody. Moody chart or Moody the diagram or the chart is in your modules. I think that is in page 8. It's in page 8 in your modules, the Moody chart. So we can solve for the friction factor by knowing the relative roughness. Ano tong relative? Relative roughness, so it is equivalent to epsilon all over d. Epsilon is the roughness of the pipe that depends on the material of the pipe. Kung PVC yung pipe, mayroon siyang corresponding roughness. Kung GI or steel pipe, any type of pipe, mayroon siyang corresponding value for roughness which is tabulated in your modules. And then it is also a function of the diameter. Okay? So yan. So merong chart yan. I will show you later on how to use the chart, the Moody chart in solving for the friction factor to be used for the Darcy Weisbach formula. Okay? Next, pwede na namang i-compute. So instead of using the Moody diagram or the Moody chart, we can use the Colebrook equation, which is a very quite lengthy formula, and it needs pwede nyong isolve yung F using the Colebrook equation. Ano ba tong Colebrook equation? So Colebrook equation is equal to, that is equivalent to 1 all over square root of F Ayan. So this is the Colebrook equation. It's an equation where we can solve for the value of F without looking at the Moody chart or Moody diagram. No. So if we know the relative roughness of the pipe, so we can solve, and the Reynolds number, of course, it's a function of the Reynolds number also. So we can solve for the friction factor F by trial and error. No? We can solve for F by trial and error, or you can use the equation solver of your calculator to solve for F